Hello, everyone. Thank you all for joining. Welcome to InRhythm Lightning Talks. I'm your host, Parag Katkar. I'm the head of consulting practices at InRhythm. InRhythm is a modern product and technology consulting firm, and we have a lot of exciting lightning talks lined up for you, which we have specially curated for all of you. Our lightning talks are hosted every Thursday at 5:15 p.m. Eastern Time, and each week, one of our practice area consultants shares their knowledge on the latest technology trends in the industry that will keep you help learning and growing in your career. And this week, we are going to do an in-depth overview of solid principles. Solid is a set of object-oriented design principle that can help you write more maintainable, flexible, and scalable code. And this talk will be presented by Tarun Saha, who is a senior software engineer with us. And Tarun won't be able to do this live, but he has recorded this session for us, which we'll get it started immediately.
Hello everyone, my name is Tarun. I'm a senior software engineer with InRhythm, and today I'm going to talk about solid principles. Now let's start with the inception and why do we need solid principles. The solid principles were first introduced to us by Robert Martin in his 2000 paper, Design Principles and Design Patterns. These concepts were later built upon by Michael Feathers, who introduced us to the solid economy. And in last 20 years, these five principles have revolutionized the object-oriented programming and changed the way how we write softwares today. Now, these five concepts make up the solid principles. Single responsibility, open-close, list of substitution, interface segregation, and dependency inversion. Now, the first question that comes to my mind, why solid, right? We often talk about writing clean and quality code, but a quality code is not limited to just a working code that gives us a desired output or a result, but also something that is reliable and maintainable. Now, this is where the solid principles come in to help us write more maintainable, understandable, and flexible software. And consequently, as our software grows, we can reduce their complexity and save ourselves a lot of headache down the Now, S in SOLID stands for Single Responsibility Principle. What is Single Responsibility Principle? It states that a class should have one thing, and therefore it should only have a reason to change. Let me repeat that. Single responsibility states that a class should do one thing, and therefore it should have only one reason to change. Now, this might seem very straightforward, but we will understand that in depth in coming slides. Now, how does SRP help us writing better software? Testing, right? Since our class is now doing one thing, hence fewer test cases. Hence, our testability has improved. Lesser functionality in a single class means fewer dependencies, hence less coupling. Last but not least, organization. Smaller and well-organized classes are easier to find than a monolithic ones. For example, let's take a look at this book. It has three properties: name, author, and text. Standard constructor, getters, and setters, and it has two methods. One is replace word in a text, which is essentially replacing a word within the book. And the other one is we are checking whether a certain word exists in the book. Now, at a first glance, it might seem that this violating the SRP principle because we said a class should do one thing, right? However, here both of this method are directly related to the book properties. Hence, they belong here, is cohesive and is in the right place. Now, these methods are not going to change in future, right? Even if we say extend the class, these methods going to remain the same. Now, with this book object, we will be able to store as many books as we want. But what good a book is if you cannot print that to a console and read it, right? So let us introduce another method, print text to console. Right? Now, this method, right, is violating the single responsibility principle. You might ask why. This print to text console contains the logic for formatting and eventually printing the text. Could be right now it's console, or if it was some other method, it would print to some other media. Now, let's say in future we might want to change the formatting, right? What happens then? Then we'll have to come back to this method, change the logic, change the business logic, and then make it work. Now you see, now this class has more than one reason to change. As per our definition of single responsibility principle, a class should have only one thing or do one thing, and therefore it should have only one reason to change. Now here we have more than one reason to change, hence it is violating the principle. How do we fix that? We simply extract the functionality, print functionality to a different class, book printer, and then we can write the business logic here. And now on, every time you want to change anything, this class has one reason to change, so is book, right? Hence, abiding by the SRP principle. Open close principles requires that a class should be open for extension and closed to modification. Now, what does this mean? Now, modification means changing the code of an existing class, and extension means adding new functionality or behavior, right? Let us understand that with an example. Now, as per the new requirement, we need a functionality to store the books in a database, right? And what we can do is go back to the same class, book printer, and we have introduced another method that is gonna do the task of storing that in the database. Now, this piece of code will include the database connection as well as storing the book into the database. Now, this method not only violates open close principle but also SRP, right? But why, right? It violates SRP because now book printer is doing two separate things, right? Hence, it has more than one reason to change. But what about OCP, right? Now, uh, as per OCP, our class should be open to extension but close to modification, right? But here, what we are doing, we needed an additional functionality. We're coming and changing, modifying the existing class. We shouldn't be doing that to facilitate an additional behavior. And more so, it is extremely common mistake to mix persistence logic with business logic. We should, at any cost, avoid doing that. How do we fix that? Fixing that is again easy. Uh, Let us define an interface. iBook persistence, which will have an abstract method, save. It's taking the book parameter and then it's going to save the book, right? Now we needed to persist the book into the into the database, right? And tomorrow we might want to store the same book into a file, right? And then in future there's something else might come, right? Now with this change, right? Now the database persistence will contain the logic for storing the book in the DB, and the file persistence will contain the logic or the piece of code for storing that into a file. Now these are decoupled, right? Anytime we want to add a functionality, say in future, if you want to add, we want to store the books into an S3 bucket, you can have a S3 persistence, implement the same interface, and override the same method. There you implement the code, and there you have it. You have a way to save the book into the S3 bucket, right? Let us see that in a driver code, a client code. You see that persistence manager has one property or dependency here, iBook persistence. Now we are initializing the persistence via the constructor, and hence we are setting this up, right? Now what happens here? Now you see the persistence manager will act as per how we initialize it. If we initialize this with the data DB persistence, then it's going to store the save book method is going to call the method on the book persistence, right? And if the book persistence is the DB persistent, it'll store in DB. If it's the file persistence, it'll save into the file. If it's an S3 or something else, it will accordingly do the task. Just a polymorphism, right? And here, see, we are able to achieve adding new functionality without having to change any of the existing classes. Hence, open to extension, but close to modification. Moving on to L in solid, it is the list of substitution principle. This is arguably most complex of out of the 5 principles. Simply put, if class A is a subtype of class B, we should be able to replace class B with A without disrupting the behavior of our program, right? This part is important. Let me underline that, is without disrupting the behavior of our program, right? We should be able to replace a class with their subtype without without disrupting the behavior of our program. In other words, LSP states that the subclasses should be substitutable for their base classes. Right? Now let's look at this example. Say we are building an app for a restaurant, and we have a menu item, right? Menu item has a price and a name, and simple getters method, where basically getting the price, right? Now we have another item which is similar to menu item, but it's a beverage item, but it has a discount running, right? And we are of course selling it at a discounted price. Now, how do we achieve that, right? Because if we do get price, it's just gonna return the price of the beverage, right? But we don't want to do that. Hence, we're introducing an additional method, get discounted price, which is gonna take in the discount percentage and do the calculation and accordingly return the price, right? Seems good. Both of this example looks perfectly fine, but let's see that in action. This is our driver code or a client code, and we're initializing a menu item with $100 is burger, and beverage item with a coke, which is also again $100. Now we want to print the prices of both the item Here you'll see we're just passing on this items into print menu item. In this method, you see what we are doing. We are first checking the item if it is an instance of beverage item, and then we are implicitly casting item to beverage item, and then we can access the get discounted price. Of course, because menu item does not have a method called discounted price, only beverage item does, which is the subclass of it. Hence, we had to check the instance first so that the casting does not fail, and then we access the method, and it prints. It'll print 100 for the burger, and it'll print 90 for the beverage item. But do you see what's wrong here? See, let me go back to the definition. Right here, it said class A, the subtype of class B, and we should be able to replace class B with class A without disrupting the behavior of our program, right? Without disrupting. Here, we are disrupting. An ideal scenario in print menu method, all we'll do is just system out print line and item dot get price. But since, however, item does not have a get discounted price, we first have to check whether the incoming instance is a subtype. If it is of the subtype, we have to cast it, and then we have to access the method discounted price, right? So this is not a straightforward substitution of a class with their subtype. Now, how do we fix that? Simply, we can do one of the ways to fix it is, of course, override the get price method in the beverage item, and then have a discount property introduced in beverage item. We can set that up with the constructor, and then within that, we can set it up to the parent class here with the super, and obviously set the discount as it coming in the constructor. Now in the get price, you see I'm accessing the get price method from the parent class and then applying the discount. Now what happens? Now we can simply get rid of the additional type check and then the casting. We can simply write the method print menu method as system.out print line item.get price. You see, now after this change, we are able to switch, or rather switch, we are able to get rid of the additional checks and additional lines of code, and we are able to replace a class with their subtype without any disruption, hence adhering to the scope substitution principle. Moving on to the interface segregation principle. Now the I in solid obviously stands for interface segregation. It simply means that the larger interfaces should be split into smaller ones. By doing so, we can ensure that implementing classes only need to be concerned about the methods that are of the interest to them. Right? What do we mean by that? Let's take an example. Now, let's look at this interface. Right? We have a bear keeper interface. Wash the bear, feed the bear, pet the bear. Right? Seems pretty okay to me, right? But you see the problem here. Wash the bear is sort of fine. Feeding the bear is also fine. Pet the bear. Strange, right? We all know the risk of petting the bear, right? Only a crazy person would do that. Now, if we define our interface like this, any class that is going to implement this interface are going to force to implement all this behavior, right? We that is not optional. Now, how do we fix that, right? Or there's a better way to do that. Let us break all these behaviors into their each individual interfaces. We have the bear cleaner, we have the bear feeder, and the bear feeder, right? Better, right? Now, let us implement a class and use these interfaces. Now here, bear cleaner implements the bear cleaner and bear feeder. Hence, it is implementing the washing the bear and feeding the bear, right? All looks good, right? Bear cleaner supposed to do just washing the bear and feeding the bear. That's all. And we are leaving the bear better stuff to the crazy person, right? Here you see, uh, when we broke those behaviors into each individual interfaces, we no longer are forcing uh, implementing classes to have those behavior, even when they're not concerned with them. Right? Hence, abiding by the interface segregation principle. Last is the dependency inversion principle. Dependency principle, uh, uh, principle of dependency inversion refers to the decoupling of software modules. And this way, instead of high-level modules depending on the low-level modules, both will depend on the abstraction. Now, we have done that before in the open close principle, but we'll go back to that example again. But let us try to understand the new example. Let's say we have a Windows 98 machine, right? Pretty straightforward. It has a keyboard, it has a monitor, right? In the constructor, you see, I am relying on the concrete implementation of a monitor, right? Here, monitor is a concrete class and a standard keyboard, right? Since I have hard coded those, right? I am tightly coupled with this the monitor and the standard keyboard, right? We don't get to change this on runtime, right? Here we don't get to take advantage of the advantage of the polymorphism that that Java provides or any other OOP language provides. How do we fix that? Simply make a monitor and the standard keyboard the abstractions. Could be interface, most likely interfaces, or it could be an extract classes as well. And then set those via the constructor. Now here, instead of hard coding, we are taking those parameters via the constructor and then accordingly setting it up. Now, how does you know help this invert with the dependency inversion, right? Here, since standard keyboard uh, is an abstraction, now we can have various implementation of it. It could be a regular keyboard, it could be a gaming keyboard, it could be a typewriter kind of keyboard, it could be XYZ, a backlit keyboard, right? And same as the monitor, it could be a standard monitor, it could be LCD, OLED, and whatnot, right? Now we have the flexibility to change the implementation without having to change the actual code here, right? We never have to change the Windows 98 machine. We just, whenever we initialize this object, we can pass in the required or the required dependent objects here. Hence, we are decoupling it, right? which is basically the inversion of control dependency inversion, right? IOC, uh, here in this case, dependency inversion. So yeah, as I said, we'll quickly go back to the open close principle where we had implemented the same. Here you see we have defined a book persistence, and then we have database persistence, file persistence, and we can have many other in future as the requirement comes. The driver code, the persistence manager is again setting it up via the constructor. Here we are not hard coding it, but whatever we pass during the runtime will be the actual book persistence. And the save book method will accordingly. See, here we're also achieving the dependency inversion. Yeah, so this is the end of our discussion today. Here are of useful links, the books that I found most useful learning solid principles from there. And that's it, open to questions.
Please make sure you mark your calendar for next week. We'll be back with another lightning talk with the latest trend in the software technologies. And thank you all once again for joining. Have a wonderful evening, and I'll see you guys next week.